Okay. So what we're going to talk about today is something called density curves, which are very important in statistics, especially one type of density curve that we're going to look at. So in the first unit, and remember, this applies to quantitative distributions of data. And remember, distributions of data is just a set of data values that we can graph, that we can perform operations on, like finding measures of center, finding measures of variability, calculating outliers. So when we get a distribution of data, you usually want to plot your data in a graph because that gives you an idea of how you can describe it, okay, when it's in graphical form. So when it's in graphical form, you can do number 2, where you look for overall patterns like the shape of the data, whether it's roughly symmetrical, skewed to the right, skewed to the left, whereabouts the center is, how spread out the data is, whether there appears to be any outliers or not. And then the third step is we can actually go and calculate some of these values. Like we can calculate a couple measures of center, median and mean. We can calculate 3 measures of variability. What are the 3 measures of variability? IQR, standard deviation, range. Excellent. And we can calculate outliers. The fourth thing, and this is going to help us actually down the road when we start getting problems where we're asked to make conclusions about data, is looking at the overall pattern of observations, that it forms a pattern that's so regular that we can kind of, there's special ways that we can work with them. And that's called the density curve. So a density curve would be like, let's say you have, don't take this down yet, but let's say you have a dot plot. I don't think this means. Let's say we had a dot plot. Okay. So here we always plot a horizontal axis for the dot plot, and then we describe whatever our data value is below, and then we have a series of dots. Well, you could end up with a series of dots that almost looks like a rectangle. That's a regular pattern. Okay? You could end up with a series of dots that looks like a very nice, what we call bell-shaped curve. You could end up with a series of dots that skews to the left or skews to the right. These are density curves because all the data values are above the horizontal axis, they're all below, and they have an area of 1. What that means is 100% of the data I'm just going to erase this, get it out of the way. 100% of the data is above the horizontal axis. And below the curve of the density curve. I'll just put curve. So like I said, they could look like this. We could have one where we've got a horizontal axis. Here we've got a curve, but it actually turns out to be a straight line. And all the data is in here. So 100% of the data is in here. So the area between these two is 1. We haven't really looked at any like this. Right? Any situations where that if we graphed it, it would look like a nice, perfect rectangle. Yeah. Sure.
How would you have something below?
Yeah, you couldn't.
Okay.
Yeah.
Okay.
You're right.
And then.
But you could have data outside the curve above. With a density curve, they're all below. Yes.
And above the curve is just like.
Like if you had an outlier. Yeah. Yeah, line of best fit we actually use for 2 variable situations, not single variable situations. Yeah.
Just a quick question. For the demonstration, you showed us the rectangle shape.
Yes.
What would you
For 5 years, I want you to randomly pick a number between 1 and 3. If you did that, and if you did it for a long, long time, eventually, the chance of getting all the numbers between 1 and 3 would be the same. So all the data would form a perfect rectangle. Can you wrap your head around that? Right, because, or let's say that, I mean, okay, let's make it simpler. Let's say whole numbers from 1 to 5, whole numbers, no fractions. And you're going to randomly pick a number from 1 to 5. And you're going to do this millions and millions and millions of times. Well, according to probability, wouldn't you get a 1 20% of the time? 1 out of 5 times? Wouldn't you get a 2 20% of the time? A 3 20% of the time? A 4 20% of the time? And a 5 20% of the time? So if you plotted them, it would make a nice rectangle. Why are you looking at me like that?
Like, what would you call the rectangle? Because it's not skewed either way.
Actually, you would call it uniform. Yes, it would be called uniform. I mean, there's not many situations. Like, let's not dwell on this too much because this is the one we're going to be dealing with the most when the data looks like this, where it's roughly symmetrical or even closer to perfectly symmetrical. These are the ones we're going to be focusing on. Many, many situations in real life model this. Okay? Not too many model this. And then, of course, we could get situations where it looks like this, or where it looks like this. But again, all the data is under the curves that I drew over top, which means that the area between the horizontal axis and the curves, or the segment, if it looks like that, is 1. Yeah, like I said, we're going to focus on this one. And we'll do that later on in this lesson. Now, this is kind of review what we talked about here, because we've really talked about where do we locate mean and median in these density curves, right? And we talked about how for the median of a symmetrical, I won't call it roughly symmetrical, I'll just call it symmetrical. The median would be right at the peak. I'm not even going to do a uniform curve. If it's skewed right, the median is going to be pulled slightly right. It will change, but not that much. Same here. It will change. It won't be at the peak, It'll be to the left or right, depending on the tail, but it's not going to pull that much. The mean, however, well, for a symmetrical curve, I'm just going to call it right now symmetrical, the mean would also be at the peak. And then it also, depending on the skew, gets pulled into the direction of the tail. Pulled in the direction of the tail and pulled more than the median, pardon me. So it'll be like here, the median gets pulled a little bit off the peak, the mean gets pulled more. Because it's not resistant to outliers. Here, the median gets pulled slightly to the left off the peak, the mean gets pulled more. So you can see, basically, this down here summarizes what we did up here. Perfectly symmetric, mean and median are at the same location, same value. But as soon as it gets a tail, the median gets pulled in that direction, the mean gets pulled further in that direction. So just as a quick example, if you were given this density curve and you were asked to locate the mean and median by letter, what would you say? What would be the best answer for, say, the median? B. And then C would be the mean. Because it's not at the peak because of the right skew, so that automatically eliminates A for both of them. The median gets pulled a little less to the right than the mean. Okay. Now we're going to focus on this one, the symmetrical one. Because it describes a lot of what happens in real life, what I said. So it looks like this. A lot of times this is called the bell curve, because we say not only is it symmetric, it's bell-shaped. When we deal with normal curves, okay, we deal with the mean and the standard deviation as measures of center and variability. We don't really talk about the median and IQR when we talk about the normal curve. So we're just going to focus on the mean at the center. Okay? And the standard deviation our standard deviation measures the spread or variability. Okay? So how we label normal curves, a normal curve graph, if you will look like this, where we will have whatever the name of the data values are. So it could be score, test score, it could be income, it could be weight, it could be height, all sorts of different variables you could have. Okay? Here we have the frequency. And notice that from The bottom left of the normal curve up to its peak and down there, I've got 7 notches. Notice the 4th notch is directly in line with the peak of the curve. That will be the mean. So if you're given a set of data, and if you're given the mean, or you calculate the mean and you're asked to graph it and it forms this kind of curve, the mean will always be, like you're going to do 7 ticks or 7 notches, the mean will always be the 4th one at the peak. Okay. From the mean, there's 3 notches to the right, 3 notches to the left. Every single notch, 1 notch, represents 1 standard deviation. Remember, we can have standard deviation above the mean or below the mean. So from here to here, if our standard deviation, like let's say the mean of some data is 20. We found the average, it turned out to be 20. And the standard deviation is 2. I would now know how to label all these notches. I put 20 here for the mean, and if the standard deviation is 2, well, as I move to the right, I keep adding 2 to the notches. So this is 22, 24, 26. And if I go down by 1 standard deviation, which I've said in the example is 2, this would be 20, 18, 16, 14. We'll practice with that, don't worry, you'll get that. It's pretty straightforward to get. Here's just a few areas where normal distributions come into play. Okay? Any kind of test score, especially standard test scores like SAT or ACT or IQ tests. Okay? I mean, test scores at this school might not be normally distributed. Okay? They might have a little bit of skew to them. But if you take a standardized test, and if you take all the people that wrote it across the world and you plot all that, it's likely going to form a normal distribution. Rolling a pair of dice. Okay. What are the possible combinations when you roll a pair of dice? What's the lowest possible sum you could get? What's the highest? 12. So everything in between, right? What do you think's the most common one you're going to get according to probability? 7. Why? Why'd you say that? It's the middle. And if you think about how many ways can I get a 7 when I roll 2 dice? 5 and 2 or 2 and 5. Think of the color, think of the dice as 2 different colors. 3 and 4 and 4 and 3. 1 and 6 and 6 and 1. So there's 6 different ways to get a 7. There's not that many ways to get the other ones. Like there's only 4 ways to get a 5. 4 and 1, 1 and 4, 3 and 2, 2 and 3. There's only, 3 ways to get a 10. 6 and 4, 5 and 5, 4 and 6. So if you were to graph that, it would form a normal distribution. Anything that we repeatedly measure, okay, which is often done, I'm sure you guys do that in science, you measure things more than once to get sort of the best measurement that you can. Well, if you measure things a bunch of times, chances are half the time your measurement is going to be a little high, and half the time your measurement is going to be a little low. And if you graph that, it's going to look like a normal distribution. Biological populations. And then you see the examples there. Okay? I mean, in general, the heights of people, the average height of a person, I don't know, if we say males, What do you think the average height of a male might be in the world? 5'8", 5'9", yeah, maybe around there, right? So we could say that's the middle, and then we would have a significant number above that height, taller, and we would have a significant number about the same number below. They would form on this normal distribution. So how do you graph it? Like, how do you set it up? Okay. Because there is, you got to be a little bit careful when you're not going to be given this all the time. You're going to have to draw your own. So the first thing you do is draw your axes and draw your 7 notches. So I always do the one in the middle, and then I go 1, 2, 3, 1, 2, 3. Now, how do I draw my curve? Do I draw a thin bell curve? Do I draw a thicker bell curve? How thick or thin do I? Well, obviously, it's going to start up here at the 4th notch. And then it's going to go like this. But how does it go like this? Don't copy this down yet. I mean, does it go like this? Does it go like this? That's sort of the art of drawing it right there. What you have to do, when you draw half of a bell curve, you're going to be going down, and at some point, you're going to feel your pencil start to move up and change direction. We call that, and this is actually something that you learn in calculus when you sketch curves, we call that an inflection point. It's kind of about halfway down half of a bell curve. That halfway point should be in line with 1 standard deviation. So when I'm going down like this, now I'm at 1 standard deviation, I should start coming up like that. And then you draw really the other side. So here, I'm at about 1 standard deviation, and now I start doing that. That's how you want to sort of draw it. So notice about halfway down each side is the same as 1 standard deviation. Because yeah, like I said, we're going to be doing, and actually we're going to be doing them in the next lesson, and we're going to be using make sure you have your graphing calculators next week. Okay? Because actually when we do normal distribution calculations, we always use a graphing calculator. I shouldn't say always, I should say the majority of the time. Because we don't actually need it today. We can do some stuff today. Okay, so as an example, we've got IQ scores. How do we label? Well, I told you how to label. I told you where to label the mean and how to label the standard deviations. So IQ scores are commonly thought to be normally distributed with a mean of 100 points and a standard deviation of 15 points. We want to label this on this normal distribution. So the first thing, make sure you guys don't miss this. Get a label. In this case, it's IQ scores or scores. Now, we've already talked about this. At what notch would you put the mean? The 4th one, in line with the peak. So this is going to be 100. So I've taken care of that. And the standard deviation gets me the value of all the other notches. So to the right, every time I go up a notch, it's 15. So 115, 30, 145, 85, 70, 55. So this should give you a good idea how to draw that curve in relation to the notches on the horizontal axis, as well as how to label it given a situation. The last thing I want to talk about with these curves today is within a certain number of standard deviations, a certain percent of the data values are within. So what do these three things mean? What this means, and we call it the empirical rule, or we call it the 68, 95, 99.7 rule, because those are the numbers that we're going to use. What that means is, I hope I can get the colors here. Let's do it like this. Stop it. Please work. No. Yes. Work. There we go. 68, when we're dealing with a normal distribution, a bell-shaped curve, 68% of all the data values will fall within one standard deviation of the mean. So remember, the whole thing is 100%, right? Everything under the curve is area of 1 or 100%. Well, 68% is going to be within one standard deviation. So over half is going to be in this section. Within two standard deviations, 95%. Within three standard deviations, almost all the data values, 99.7, just a few will be outside, either low or high. What's that? Don't worry about those. We're not worried about those. We're focusing on these values here. Yeah. So like if we go back to our IQ scores, in general, we could say, well, 68% of IQ scores are from 85 to 115. So that's what we're generalizing to the population. So the population in the world, 68% of all the people in the world have an IQ between 85 and 115. 95% have an IQ between 70 and 130. 99.7, pretty much all people in the world have an IQ between 55 and 145. And then you've got that rare group outside, either low or very high. Okay. So when we do problems that involve normal distributions, what we want to do is we want to draw and label a normal curve. And remember these symbols. Mu means population mean, and sigma means standard deviation. Then we perform the calculations that were asked to, depending on the question. And then we answer the question in context. So in context to whatever the problem is. So for these last two examples, let's just look at, we're talking about the IQ scores again. And you've got to use these numbers to help you figure these answers out. So IQ is normally distributed, so 1, 2, 3, 4, 5, 6, 7. I'm going to get my curve right away. My peak's up here. Halfway down, I start to go out. Halfway down there, I start to go out. So that's not great. Could have done better. That size. My mean is 100. And then the 3 ticks to the right, or the 3 notches to the right, are 115, 130, 145. The 3 notches to the left of the mean are 85, 70, and 55. And remember, these are scores, or more specifically, IQ scores. Now we want to shade the problem. I want to know approximately what percent of test takers, the entire population who has taken an IQ test, has a score of at least 70. So here's my shading. I want to know what percent is that. You've got to use the numbers up top. Sorry, somebody? 97? How'd you get 97?
95 is 2 standard deviations, and you're removing 1 standard deviation, which is halfway between 95 and 99.7. 97.4.
97.
Oh, 4. Am I?
No, yes, absolutely you are. So you're saying 99.7 is within 3. And then you're removing half between 95 and 99.7. Yes, that reasoning makes sense. Okay, and that would work. A similar reasoning would be this. Thank you. I've never thought of that before. That's good. I know this. How much is this area? 95%. How much of the remaining data do these two make up? If this is all 95% in here, what percent of the data do these two make up? 5%. And half of them? 2.5%. So this would be 5% divide 2, which is 2.5%. And so our answer would be 95% from 70 to 130 plus 2.5% from 130 up gives us 97.5%. The only thing with your reasoning, Roshni, is that you wouldn't have been accounting for the small number outside, right? But otherwise, that's good thinking. Okay. Are we sort of getting the idea of this? So that's how we got to use the math in this case. All right, last question. We're going to do the same thing. So 1, 2, 3, 4, 5, 6, 7. No. So 100, 115, 130, 145, and then on the left side of the mean, 85, 70, 55. Those are our IQ scores. Now this is a little bit of a different question. What test score is at the 84th percentile? Doesn't that mean that what test score is 84% of all the test scores the same or below? That's what the 84th percentile is. So it's obviously like this. Think about it this way. What percentile would that one be? That's good. I mean, that one's kind of obvious. So the 84th is going to be somewhere around here. But the question is where? This is where you've got to use the percentages again. So we know the 50th is here. What would these be? How did you get that? Sorry, say that again.
Half of 68 is on either side of it.
So, yeah, so what you're saying is between these two here is 68. So these two little sections here are 32. Sorry, 34. 34% and 34%. So that means this must, if this is the 50th, this must be the 50 plus 34, right? So this must be the 84th percentile. Which means that's the value I'm looking at, and that value is 115. So a score of 115 IQ score is at the 84th percentile. So we can answer quite a few questions knowing the 68, 95, 99.7 numbers. So we can't answer all of them. Because what if I asked you this, if I said, what percent of the scores of all IQ test takers is above 117? Can't use these numbers here, can you? Because 117 is not one of our notches, so we can't use those percentages. So we need a different method, and it's actually calculus. But we're not going to perform the calculus. Our graphing calculator is going to perform the calculus for us. Okay, so don't freak out.